Thank you, everyone, for staying for the second talk. So in this talk, I'm going to be presenting GIFT, which is a coupon-based throttle and reward approach for maintaining fair and efficient I/O bandwidth management on parallel storage systems. So that sounds like a mouthful, but I'm going to break it down a little bit so that it's simpler to understand. So I'll start by presenting the key idea behind GIFT. But before we get into the key idea, I'll present some background. And this might be a little bit of a repeat of the previous talk, but just pay attention to this because it's slightly different. So we have data-intensive parallel applications which are running on these HPC systems. And these applications perform a lot of I/O. This I/O can be in the form of checkpoint and restart or data analytics I/O. And this I/O is in phasal behavior. So we have compute phase, and then we write it down or read whatever new data that we need. So we have the I/O phase, and then we have the next compute phase, and then the I/O phase after that. So this type of phasal behavior exists for these data-intensive parallel applications. And from the compute system on which they're running, they perform their I/O to the parallel storage backend system. So this parallel storage system is actually performing I/O for all of the concurrently running applications. And while they have their isolated compute resources, the I/O resources are shared. So as we saw earlier, if we look at a general Lustre-based system, then the I/O backend has several components. So the two components at the top are the MDS and the MDTs, which is the metadata servers and the metadata targets. These two components serve and manage the metadata operations. But the main components are the OSSs, or the object storage servers, and the object storage targets, which are the OSTs. So as I mentioned earlier in the previous talk, OSSs are the ones that manage the I/O request, and the OSTs are the ones that actually store the I/O data. Okay. So we know that parallel applications are performing their I/O in parallel, and they're all using their shared resource. So this can, for obvious reasons, cause unmanaged and unpredictable I/O interference from different applications to each other. So in this example over here, let's say we have 5 applications, A, B, C, D, and E, and we have 2 OSTs. And on the first OSTs, we have application A and C performing their I/O. And on the second OST, we have applications A, B, D, and E. So as we can imagine, on OST 2, we have twice the amount of contention as OST 1. And that's why application A, which is performing I/O on both of these OSTs, would actually experience a slower I/O progress on the second OST. So that is demonstrated by this figure over here, where if we look at the vertical tower as the overall bandwidth, we can say that on OST 2, the bandwidth is actually divided among 4 different applications, while on OST 1, it's only divided among application A and C. So application A ends up receiving 50% of the bandwidth on OST 1, but because it's bottlenecked by OST 2, essentially it's only using 25% of the bandwidth on the first OST, and the other 25% we refer to as the bandwidth waste, because that 25% does not contribute towards the application finishing its I/O phase any faster. And that we can look at in more detail in this example. So let's say we have this traditional scenario where we have 2 time steps. At the first time, application A is performing I/O on all 4 OSTs, and application B is performing I/O on the last OST. So the other 3 OSTs are giving 100% of their bandwidth to application A, but it's constrained by the very last OST. So we'll say that 50% of the bandwidth on all 3 of the other OSTs is not being used effectively, because essentially application A's, it's not contributing toward application A finishing any faster. And then at time T2, we have this other scenario where we have applications B, C, and D. And again, we see that application C, while it gets 100% of the bandwidth on the third OST, it's still, half of it is still wasted because it's being shared with B. So we want to be able to maximize this, we want to be able to minimize this bandwidth wastage, but we still want to remain fair to applications that are actually causing this bandwidth wastage. So a simple scenario, for example, at time T1 would be to give 0% of the bandwidth to application B, and then A would have all the bandwidth and we would have 0 bandwidth wastage, but that would be extremely unfair to B, which is why with GIFT, we do this coupon-based throttling and reward approach. So at time T1, we would throttle application B, let's say by 25%, and we would issue a coupon to application B for that much amount. And then at time T2, we would actually redeem that coupon. So we see that at time T1, the bandwidth waste goes down to 25% on all of the OSTs, while on time T2, we still have some bandwidth waste, but overall, our bandwidth waste was minimized. And we were still fair to application B, because of the fact that we were able to give back its bandwidth at a later point. And we will see how Gift actually, what kind of insights Gift uses to enable this. Okay, so the coupon-based I/O bandwidth bandwidth allocation appears promising, but as you can imagine, there are a lot of challenges for this, and there are also a lot of favorable characteristics. So first, we'll look at the favorable characteristics. So HPC applications are infamous for their monotonic behavior. They appear again and again, they appear frequently, and they exhibit similar I/O behavior across the different runs. And this monotonic behavior is important if we want to do this coupon-based throttling and reward, because we want the application to come back if we want to be able to reward it back at a later point. Otherwise, if it doesn't come back, then we were simply unfair to it, because we throttled it, and then we were never able to give it back anything. So in the first figure over here, we look at the number of appearances of HPC applications. So the x-axis shows the number of appearances, and the y-axis is the CDF. And we look at 3 supercomputers, Stampede 2, Mira, and Theta. And we see that over 80% of the jobs appear at least 5 times or more, which means that HPC applications are highly repetitive. And not only are they highly repetitive, but they also appear frequently. So here we plot the inter-arrival times of these applications. And we see that over 70% of the applications actually appear within 5 hours of each other, on Mira and Theta both. So not only are they repetitive, but they're appearing frequently, which means we have even more power to do this coupon-based bartering. And lastly, we need them to have similar I/O characteristics as well, because if they keep changing their I/O characteristics, then the coupon management becomes very difficult. But we see that HPC applications actually have very predictable I/O. So here we have 4 metrics. We have the total amount of data read during a run, total amount of data written, the number of sequential reads, and the number of sequential writes. And on the x-axis, we have the standard deviation of all 4 of these metrics. And on the y-axis, we plot the CDF. So here we see that over 75% of the applications have a standard deviation of 0%, which means that they're performing exactly the same amount of reads, exactly the same amount of writes, exactly the same type of sequential I/O from one run to another, and as many times as they appear. So because they have this type of monotonic behavior, we can really leverage this behavior to be able to be fair to them in a longer time frame than just at instantaneous time frames, which actually waste a lot of bandwidth, as we saw earlier. In terms of challenges, the main challenge with Gift is the OST level I/O contention. So the OSTs have different levels of contentions on each of the individual OSTs, but a good HPC application, which is performing good parallel I/O, wants to actually use multiple OSTs in order to exploit their parallel power. Obviously, a simple solution would be to just do I/O on one OST, but that essentially means you're doing serial I/O, and that's not going to give you any, that's going to make I/O an even bigger bottleneck. So here we have these 2 figures, where we look at the engaging and Stampede 2 supercomputers. And on the x-axis, we have different configurations. So 2x4 here means the IOR experiment that we conducted was running on 2 nodes and spanning 4 processes on each node, so 8 processes in total. And all of these processes are performing the exact same amount of the I/O and the exact same type of I/O. And we see that as the number of processes increase, the variation in I/O time, which is shown on the y-axis, increases considerably. And this means that from one process to another, each HPC application is seeing different amount of I/O time. And this is also illustrated in the 2 figures on the right, where we have the 2 OSTs. And again, we see if on OST 2 there are 4 applications running, then this creates a bandwidth waste on OST 1, because that bandwidth is not contributed towards application A's I/O progress. So why not use it for some other purpose which can speed up other applications while minimizing the system's bandwidth wastage? So this is the main challenge with Gift. We want to perform synchronous I/O progress. And by synchronous I/O progress, I mean we want to ensure that each application on each of the OST on which it is performing I/O gets the exact same bandwidth. And for doing this, we want to also make sure that we maintain the efficiency of the system bandwidth, which means we maximize the effective system bandwidth or minimize the wasted bandwidth. And we also want to maintain fairness across fairness in terms of the bandwidth allocation of applications, because it's very easy to maximize system bandwidth if we're not fair. But we have to be fair to the HPC applications, because we don't want to slow down any single application's I/O progress, which can cause many other issues in the scientific domains. So to this end, let's look at some bandwidth allocation policies which one can imagine we can deploy. So the first one is Per-OST fair share, or POFS. So with POFS, we're going to divide the bandwidth equally among all the applications that are running on each of the OSTs. So here on OST 1, we would divide bandwidth equally between A and C. OST 2, we would divide it between A, B, D, and E. OST 3, we would divide it equally between A, B, and D. And this is a simple thing to do because the management is only at per-OST level. But here, clearly, we see that applications A, B, and D are bottlenecked by the second OST because they're getting only 25% of the bandwidth on each of the OSTs. This means that their bandwidth on OST 1 and OST 3 is actually wasted. So here we see that on the OST 3, all three of them are wasting 8% of their bandwidth, while on OST 1, application A is wasting 25% of its bandwidth. So this means that while this policy is fair, because the most fair thing to do is to divide the bandwidth equally, it does not ensure synchronous I/O progress, and it has a lot of bandwidth waste. So another policy that we can look at is basic synchronous I/O progress. So with this policy, we want to actually enforce that there should be synchronous I/O progress, and there should also be fairness. And we can do this at the cost of bandwidth wastage. So here, first, we start out by giving everyone their fair share. So we see that application A, B, and D are bottlenecked by OST 2. So on both of the other OSTs, OST 1 and OST 3, we give them 25% of the bandwidth because that is their fair share. They don't need more than that on the other OSTs because that's not going to contribute towards their I/O progress. Then we see that on OST 1, we're still left with 75% of the remaining bandwidth, and application C's allocation would be 50% because its fair allocation is 50%. And whatever is remaining for 1 and 3, we divide it equally among all the applications. So here still we have bandwidth wastage because application A on OST 1 and the other 3 on the third OST are still seeing bandwidth wastage. So while this policy is fair and synchronous, it still has a lot of bandwidth wastage. And the last policy that we look at is minimum bandwidth wastage. So with this policy, we actually do what we want to avoid doing at any cost, which is to be extremely unfair to any application. Here we are unfair to application E, and we will give it 0% of the bandwidth. This means that A, B, and D can actually expand on OST 2, and they can get their full fair share on OST 3 as well. And on OST 1, we can give the remaining 67% to application C. So here, everyone is using their bandwidth perfectly fine, and all of them are performing synchronous I/O. But of course, this is extremely unfair because now application E is not getting treated fairly. So as you can imagine, it's difficult to maintain a balance between these three goals. And with GIFT, this is exactly what we want to achieve. We want to achieve fairness, we want to achieve synchronous I/O progress, and also we want to minimize the bandwidth wastage. So these are the three key ingredients of GIFT. One is fairness. So we want to break away from the concept of instantaneous fairness, which is actually causing the system to have a lot of bandwidth wastage. And instead, we want to have this long-time fairness concept because these applications are coming back and back. So we can actually be fair to them over the long time period so that their average I/O runtimes over all of these runs still remains the same or it even improves. So we use this barter system for the unfair treatment, and we award them compute hours for unfairness in I/O bandwidth allocation. So this we refer to as the system's compute hour regret budget. And obviously, we want to minimize the system's regret at any cost because we don't want to be giving out compute hours to these applications for no reason. And as we will see in our evaluation, this number is actually minimized as much as possible. It's just there for the system to give the system an incentive to be fair to the applications. The second ingredient is the synchronous I/O progress. So we know that GIFT's initial allocation should be the same as BSIP, which is basic synchronous I/O progress, which was the second policy that we saw. With BSIP, it does fair and synchronous allocation for all the applications initially. And then GIFT builds on this, making subsequent readjustments to ensure that this property is preserved, which is the property of synchronous I/O progress. And the last ingredient is to minimize the bandwidth wastage. So in minimizing the bandwidth wastage, we actually will need to throttle some of the applications and expand the allocation of the other applications. And this obviously creates the issue of unfairness. And we will give out coupons to these applications and then reward them at a later time by redeeming them. And how exactly will we do that? So here's the overall flow of Gift. So at every decision instance, we perform the BSIP bandwidth allocation. Then we have two steps. One is to actually redeem outstanding coupons. So we go through the allocations of all of the existing applications, and we see if any one of them has any outstanding coupon. If there is, and if it is possible to redeem it, then we will redeem it, and I will define the criteria for redemption later. And the other possibility is to determine, the other step is to determine the throttle-friendly applications. So I'll explain what exactly I mean by throttle-friendly applications. But these are applications which are easy for the system to throttle because the system is fairly confident that it can give back coupons to them at a later point. And then the next step is to allocate the bandwidth optimally. So now we need to perform optimal bandwidth allocation such that it minimizes the bandwidth wastage. And then once we're done with that, if any applications are throttled, we will give them coupons, and we will decrease their redemption rate. Okay, so the first step is to identify throttle-friendly applications. So for this, we use a receding window approach, where initially, when the application is initialized, it has a perfect redemption rate of 100%, as is seen in the top bar, where the 100% is actually n, where n is the number of coupons that can be issued to them at maximum. And as more and more coupons are issued to them, their redemption rate keeps going down. And as long as the redemption rate is greater than the tau factor, as is shown with the dashed line, they are considered as being throttle-friendly application because the system is fairly confident that if the redemption rate is greater than tau, then it will be able to give coupons back to these applications at a later point. But once the coupons, a lot of coupons are issued and the redemption rate goes beyond, underneath tau, then in that case, the system stops issuing coupons to that application because that application is no longer throttle-friendly. But of course, once an application becomes throttle-friendly, it can still, non-throttle-friendly, it can still become throttle-friendly. For example, if the issued coupons get redeemed at a later point, then the same application as shown in the last bar can become throttle-friendly. So the set of non-throttle-friendly and throttle-friendly applications keeps changing from one instance to another, and no application is permanently labeled as being throttle-friendly or non-throttle-friendly. It's just that we have this factor of tau because we don't want to keep blindly issuing coupons to an application if it's not going to be able to redeem it at a later point, because that's going to cost system compute node hours. So the next step is to actually carefully perform the coupon redemption. So we don't want to redeem the coupons when it actually costs us throttling other applications, because that will result in a zero-sum game. So every decision instance, we go through the outstanding coupons of existing applications. And if all of the OSTs on which an application is performing I/O has a bandwidth gap, then that application is a good candidate to redeem coupons for. So I'll explain exactly what that means using this example. So in this example, we have two OSTs. OST1 has 3 applications, and OST2 has 4 applications. And B is doing I/O on both of the OSTs. So clearly, B is bottlenecked by OST2, and it receives only 25% of the bandwidth on OST2. This means we can give it 25% of the bandwidth on OST1. And applications A and C have their fair share allocation of 33%. This leaves a bandwidth gap of about 8% on OST1. Now, we can use this bandwidth gap in 2 ways. One is to divide it equally among A and C. And A and C can use it very efficiently because they're only performing I/O on that OST. So they can do it synchronously. So this means that both of them get to have 38% of the bandwidth. On the other hand, if we see that application A has an outstanding coupon worth 15%, then we can actually allocate all of that gap to application A. This is not unfair to application C because it's still getting its fair share of 33%. But now we're redeeming applications A's coupon without throttling B or C. So this is the general idea. And one might argue that if spare I/O bandwidth is available, then naturally that would have been allocated to A and C anyways. So how are you exactly reducing the bandwidth wastage? And to demonstrate that, we'll look at this example. So here on the top, we have allocation using the BSIP scheme. And on the bottom, we have allocation using Gift. So we have 2 OSTs. On the first OST, we have applications A and B. And on the second OST, we have only application B. So as we see with BSIP, because B is bottlenecked by the first OST, on second OST, its effective bandwidth is only 50%, and the rest of the 50% is actually wasted. So with Gift, we notice this, and we say that let's give application A a coupon worth 15% and then throttle it by 15%. So application A is now only going to receive 35% of the bandwidth, and this means that we get to expand B by 65%, which means it also expands on the second OST, and now the bandwidth waste is reduced to 35%. And this is at instance K1. Now let's look at another instance, K2, where we have similar scenario as before, where we have on OST2, we have 4 applications, and OST1, we have 3 applications. So with BSIP, as before, we would see that B is bottlenecked by OST2, so we will give a 25% bandwidth on OST1, and then we will divide the remaining bandwidth equally between A and C. But with Gift, as we saw before, we noticed that application A has an outstanding coupon, so we can give 9% of the bandwidth to application A, while C still gets its fair share of 33%. And then lastly, at another instance, again, we see similar scenario, and this time we notice that application A's outstanding coupon is only 6% remaining. So we give that 6% to application A, and we give the remaining 6%, remaining 3% to application C. So in the last scenario, application A has 39% of the bandwidth, and C has 36% of the bandwidth. So as you notice, in both BSIP and Gift, both do perfectly fair I/O allocation, bandwidth allocation, and both do perfectly synchronous I/O progress. But with Gift, we have actually saved the system bandwidth by 15%. And this is just for 2 OSTs and a few applications. But as you can imagine, there are tens of hundreds of OSTs and tens of hundreds of applications performing I/O in parallel. So there are a lot of these gaps which can be leveraged to improve their performance considerably. Okay, so the last step is to actually perform optimal I/O bandwidth allocation. So this essentially accounts to maximizing the linear programming equation, which is shown on the top left corner. So we maximize over all of the OSTs and over all of the applications that are running on those OSTs, the bandwidth allocation B of I, where I is the application I. And this equation is subject to a bunch of constraints. So the first constraint is that all I/O requests of an application issued across all of the OSTs should get the same bandwidth for synchronous I/O progress. And we enforce this as a constraint. The second constraint is that the final bandwidth allocation should be fair, and if an application is deemed throttle-friendly, then the final allocation can be slightly less than the fair allocation because we'll issue it a coupon for that amount. And lastly, all OSTs are constrained by their full capacity. So when we maximize this equation, we're actually minimizing the bandwidth wastage across the entire system for all of the OSTs. So in the paper, we have the mathematical formulation for how we determine the throttle-friendly application, the formulation for this optimization function that I just showed. We also have the discussion of the design parameters and their impact, and we also have all the details of the Gift prototype implementation, which I'll show next in the evaluation section. Okay, so for evaluation, we perform 2 types of evaluation. One is a fused-based prototype implementation, and the other one is a simulation-based implementation. So for the fuse-based prototype implementation, we have the system of 64 OSTs and 192 object storage clients, or OSCs, and we run 250 applications, real HPC applications on this setup, using the parameters and job characteristics from Stampede2, Mira, and Theta supercomputers. And these characteristics include number of nodes, compute time, amount of I/O, job scheduling using backfilling, and job inter-arrival times. And we run this entire system, and we get a bunch of metrics, as we will see later. And for the simulation, we do a real simulation setup. So we, again, get the job characteristics from the same supercomputers, but we don't scale them down like we do for the prototype. We run them for a 1-month simulation using the real characteristics. And we compare Gift against 7 other strategies. So the first 3 mentioned at the top are the ones I already discussed. Per-OST fair share is our baseline allocation because it's the easiest to manage and it's very fair thing to do. The second is the basic synchronous I/O progress, or BSIP. Third is minimum bandwidth wastage, or MBW. And then we have other 4 throttle and expand based heuristic applications, which don't do throttle and expand the way that we do it for Gift, but they have other heuristics, such as throttle randomly, or throttle the smallest application or the most frequent application. Smallest and most frequent because those are the applications which are easiest to give back to in forms of coupons if they were to return and come back. And lastly, we also look at expanding small applications. So the first set of results that we look at are the prototype results. And we show that Gift improves system I/O bandwidth, mean application I/O time, and runtime. So we have 3 figures over here. For each of the figures, the x-axis is the 7 different strategies. And the y-axis shows different performance metrics, which are normalized to the POFS performance. So the first metric is the system bandwidth improvement. And this is the improvement in the effective system bandwidth, or the improvement in the reduction of the bandwidth wastage. And as one would expect, MBW, which is minimum bandwidth wastage, has an improvement of 103% compared to POFS. But of course, this policy performs very badly for all of the other metrics, as we will see later. And Gift has an improvement of over 15% as compared to other strategies. So in this area, Gift performs very well. The second figure in the center, we look at the mean application I/O time for all of the applications. And here we see how bad MBW performs in terms of fairness, because it has an improvement of negative 26%, while other strategies have an improvement of 2 to 4%, but Gift improves the I/O time by about 10%. And this also translates into runtime at the end, where Gift is able to improve application runtime by 2.5%, which is much more than the other applications. Next, we look at the fairness results with Gift. So with these plots, we'll first look at the plot on the left. The x-axis shows the application IDs. So we ran 250 applications, so we have the IDs of 250 applications. And the y-axis shows the improvement in their I/O time compared to POFS. So if this improvement is positive, then we say that this application was treated fairly, because POFS does fair allocation, so there is nothing more fair than that. And if it's less than 0, then that means that it was not treated as fairly. So here we see that Gift is at least as fair as BSIP. So Gift is shown in the dark navy line, where we see that for most of the applications, Gift actually improves performance considerably compared to POFS, as compared to MBW, which actually ends up degrading most of the application performances considerably. And with Gift, in the second plot on the right, we look at the runtimes, and we see that this improvement also translates into runtime. And when we look at the percent of applications which actually have greater than 0% I/O time degradation, Gift has the fewest percent of applications which see a degradation at 30%. And you might say that 30% is still high, but the average I/O time degradation just among these degraded applications is only 1.2%. And this might not be a direct result of Gift policies, because the simulation runs for a long time. Sorry, the prototype runs for a longer time. So different policies means that different applications get scheduled with different applications. So that also introduces some I/O time variability. And next, we look at the simulation-based results. And with simulation, we see similar results as prototype, but just better, because we have a longer time window and a larger system scale. And we see that simulations, we also see I/O time improvement, runtime improvement, effective system bandwidth improvement, and most importantly, system throughput improvement. So while Gift was not focused on system throughput, it is able to improve this system throughput because of the fact that it reduces the application I/O times and uses the bandwidth more effectively. So system throughput improvement is of 2%, which translates into considerable node hours. Next, we see how different I/O behaviors affect Gift. So here we have 3 plots. The first plot shows the I/O time improvement based on the number of I/O intervals. The second plot shows the size of I/O per rank, and the last one shows the number of application appearances. So with these figures, we want to see if Gift is actually favoring a certain application characteristics more than the others. And we see that across the board, the I/O time improvement is actually positive. So Gift is not biased towards any particular application characteristics. And more importantly, it's not biased against any particular application characteristics. It just leverages how the applications are performing I/O together and uses that to manage the bandwidth more effectively. And the last thing that we will look at is how the system's regret budget pans out. And here we have evaluation for both the prototype and the simulation. And the x-axis shows the amount of node hours that had to be given out, the cumulative amount of node hours, as a percent of time. And with simulation, we see that it stabilizes and it's very low. But because the prototype implementation is a simpler figure to look at, so that's the one we'll focus on here. So here we see on the y-axis, we have the outstanding node hours that were given out as a % of total node hour improvement because of the improvement in system throughput. And we see that overall, the node hours that were given out was less than 0.08% of the amount of system throughput that we gained. So in most cases, Gift is able to give back to the applications whatever coupons were issued to them. It's just a few applications which it was not able to give out. And this was when it was giving out these node hours at per hour interval. If we expand this interval to, let's say, a week or a month, then we would expect even fewer node hours to be given out. And lastly, you might say, what is my Gift in all this? And the answer to that is that Gift is open sourced on our GitHub page at the link that is given, and you can also access it using the QR code. We have our complete fuse-based prototype, which is available at this link. Yeah, thank you.
Questions?
Sorry.
Yeah, hi, Tom Telpe, Microsoft. I think it's great. Storage quality of service is a very underrepresented topic, and I'm glad to see you working on this. I have two questions. The first is, it seems the coupon it somehow reduces all IOs to be roughly the same cost. It assumes that the problem is purely bandwidth. So it seems to simplify the problem to say that this is sequential IO, read or write doesn't matter, it all costs the same. Why didn't you go to a deeper level about the actual cost or the actual latency, for instance, of each operation? Why didn't you separate read and write in particular?
Right, so for our actual implementation, we do time-divided bandwidth allocation because we don't want the fairness results to be influenced by whether an application was doing reads or writes or random I/O or sequential I/O. So that would obviously affect.
The cost of each operation is quite different.
Sorry?
The cost of each operation is quite different potentially. So
right, so the bandwidth that they actually end up observing might be very different. But because we do time-divided bandwidth allocation, so we give them a certain amount of bandwidth that they can use. And within that period, they might not be able to use it based on the kind of operation that they're doing. But we don't want to concern ourselves with that. We just give them a certain chunk of the resource, which is equal for all of the jobs. And how efficiently they use that resource is based on, obviously, their I/O characteristics. Yeah.
Okay. My second question is, who's the coupon manager? How does it get the system-wide view? For instance, you had 3 OSTs, and each one had policies, and they all fed back to a single application. Is there a single global entity in the network? And if so, how does it get that global view?
Right, so for a fuse-based implementation, we actually have this transparent view of what applications are running on each of the OSTs. So in a traditional Lustre-based file system, this information is not available. But with the file system that we built, we actually made this information available at the OST level. So the MDS receives all of the I/O requests. And once it opens the file descriptor, then the MDS is not concerned with exactly what is performing I/O at the individual OSTs. We need to be able to track the I/O at the individual OSTs. So the OSTs need to actually have this information. So there is a global entity which communicates with all of these OSTs. And at every decision instance, let's say 10 seconds or 15 seconds, it receives this information from the OSTs, makes its decision over the LNet, which is the
and
network
rebalances
specific.
the coupon accounts.
Right, and then it sends back whatever calculations that it does.
Okay.
Yeah.
Thank you.
Yeah. Thank you for the question.
Yep. I think we're about out of time, so any more questions? So with that, let's thank our speaker again.
Thank you.